Hello everyone. Today we are going to revise the periodic classification. Okay. So now in the periodic classification, the important questions are based on what the variation of periodic properties across the periods and down the group. That means what now here across the periods meaning what from left to right in the period, how the variation of periodic properties will be there and how the periodic properties vary from top to bottom in a group. These two areas are very important. So generally, what are the periodic properties? What we have discussed are atomic size, ionization enthalpy, electron affinity, electronegativity. These all properties are what periodic properties. Suppose I'm taking here atomic radius or atomic size. Okay, atomic radius, then ionization, ionization enthalpy, then electron affinity, then electronegativity. These all properties we have discussed here. Remaining we have discussed the reducing properties and what are oxidizing properties. This all we studied. So first of all, we have to understand about these properties. These are very important periodic properties. The variation of these properties across the period from left to right and down the groups means from top to bottom in the groups, how they change. This point we have to understand mainly. Tell me how atomic radius vary, how atomic radius varies across the periods from left to right, increases or decreases. Generally it decreases. Generally it decreases, but here 100% it will not decrease non-stop from what here first group to 18th group. There won't be decrease in atomic radius completely. So we say generally it decreases. Generally what now here the atomic radius decreases from left to right in the period. So across the period means what now left to right in the period. Next, now we'll discuss about this. Why we wrote generally decreases, why not always it will decrease from left to right, we'll discuss. Next, how ionization energy will change from left to right in the period. It will increase or decrease. It will. It generally as size is decreasing, ionization energy should increase. So generally increases. Arrow mark upwards indicates what? Increases. Yeah, arrow mark downwards indicates what? Decrease we're taking. So here what happens now? Atomic radius will decrease from left to right in the period. Therefore, ionization energy will increase. So whether ionization energy continuously increase across the period or not, we'll discuss. Okay. Next, electron affinity. Electron affinity. So whether electron affinity increases or decreases from left to right in the period, electron affinity also increases. Okay, whenever ionization energy is increasing, electron affinity also will increase. These are all general points only. Remember, 90% things we will take into consideration. Any statement, any scientific statement is not 100% true. Okay, there will be exceptional cases for every statement. So here we are saying that ionization energy increases from left to right in the period. That is general statement, that's all. Not 100% true for all the elements. There will be irregularities here. There will be irregularities here and there. That means what? There will be what? Anomalous behavior for some elements. Okay. And also there will be some exceptional cases. These are all things we have to understand. So generally we are taking statement that electron affinity or electron gain enthalpy will be increasing from left to right in the period because of decrease in size. Next, electronegativity also increases. Whenever size is decreasing, these all properties should increase generally. So electronegativity also increases from left to right in the period. Is that clear? Next, if you take groups from top to bottom in the groups, so we have to say down the group. What we have to say? Down the groups. So down the groups we say and across the periods and down the groups we have to say. So across periods we have understood here. Now down the group from top to bottom, what happens to atomic radius? Tell me. Atomic radius will increase or decrease? Atomic radius must be increasing from top to bottom. From top to bottom in a group, atomic radius or atomic size increases. Atomic size increases. This upward arrow indicates what here? Increasing nature. So how does atomic radius vary from top to bottom in the group? It increases. Okay, why atomic radius is increasing from top to bottom? Due to increase in the number of shells. From top to bottom in any group, number of shells, number of orbits will be increasing. Whenever the number of orbits increases, when the number increases, what happens? The size also will increase. Then atomic radius will increase. So atomic radius increases from top to bottom in a group. Okay. Next, ionization energy. How ionization energy vary? How does it vary? How does it vary from top to bottom in the group? As atomic radius is increasing from top to bottom, as atomic radius is increasing from top to bottom, what happens to ionization energy? It must decrease. It must decrease. So ionization energy will be decreasing from top to bottom. From top to bottom in the group, what happens? Ionization energy will decrease. And what about this electron affinity? Electron gain enthalpy. Electron gain enthalpy will increase or decrease? Will decrease, because atomic radius is increasing from top to bottom. Therefore, ionization energy decreases, electron affinity decreases, and also electronegativity decreases. Electronegativity also will decrease from top to bottom in the group. So electronegativity, electron affinity, ionization energy, and atomic radius. These are all properties. Okay, increase or decrease here. Atomic radius increases from top to bottom, whereas the remaining three properties will be decreasing from top to bottom in the group. And across the period, atomic radius is generally decreasing, and ionization energy increasing, electron affinity increasing, electronegativity increasing. So what we have to understand here now, ionization energy generally, and electron affinity, electronegativity, electron affinity, and ionization energy. These all properties are inversely proportional to what? Atomic radius. Atomic radius generally. Okay, this point mainly keep in mind. Now we are going to discuss the variation of what now these all properties. Okay, with reasons. Reason is very important than what the statement here to understand. So the understanding about reason for each statement we must be knowing. So first point what we have discussed here, atomic radius. Atomic radius is decreasing from left to right in the period we said. Now suppose you take second or third period elements you take. Third period elements. In the third period elements, what are the elements here? Sodium, magnesium, aluminum, silicon, phosphorus, sulfur. Okay. Next, what here? Chlorine, argon, all these elements here. Sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. Now here, from sodium, this is first group now here, group 1. It is group 18. Group 1 to group 18, if you take, it is group 13, aluminum. Okay. Now what happens is that from alkali metal to halogen, the size will decrease. The size will be decreasing. Atomic radius decreases from where to where? From first group to 17th group. Here it is group 17. Halogens for group 17. So now sodium to halogen. What happens now? Size will decrease. Then from 17th group to 18th group, size will increase. Size will increase. Remember, the size will be increased to 18th group. That means what? Between chlorine and argon. Between chlorine to argon, what happens now? The size will be increasing. That means from 17th group element to 18th group element. From a 17th group to 18th group, the size will increase slightly. Okay, so the size will be increasing because among the what here, inert gas elements, 18th group elements, the attractive forces are van der Waals attractive forces. Between argon and argon, what will be there? Van der Waals attraction, weak van der Waals attractive force will be there among the inert gas elements. So whenever van der Waals force of attraction is there, the radius will be called van der Waals radius. Between argon atom, inert gas atom, there will be weak attractive force. They are not touching, they are not overlapping. Argon atom are not touching each other and also not overlapping with each other. That's why there will be weak van der Waals attractive force between the inert gas atoms. So due to this weak attractive force called van der Waals attractive force between the atoms of inert gases, the radius of inert gases will be considered to be van der Waals radius. That van der Waals radius will be greater here. That means what? The size of argon will be greater than the size of halogens. Is that clear, ma? But here, if you take chlorine and chlorine atoms, two chlorine atoms, if you take to form molecule, Now chlorine atom will overlap with chlorine atom. No? Chlorine atom will be overlapping with what? Chlorine. Suppose if you take here Cl and Cl, they will overlap. Cl, Cl. They will overlap to form what now? One bond. This bond is called covalent bond. That's why here in case of chlorine, what we are taking? Covalent radius we are taking. Covalent radius. But in case of argon, both are away from each other. They are not touching each other, not overlapping with each other. Now the internuclear distance is what? More. Between this nucleus, internuclear distance is more. Half of this internuclear distance is called van der Waals radius. Van der Waals radius. And here half of the internuclear distance between two nuclei. This is called covalent radius. Covalent radius. So generally van der Waals radius will be greater than what? Covalent radius. Van der Waals radius is greater than covalent radius. So generally, inert gas atom will be having larger size than halogen. That point keep in mind. Next, here what we have to say now here, the atomic radius will decrease from first A group element to seventh A group element. Seventh A group element is what? Halogen. But halogen to inert gases, the size will increase. But if they ask you which one is highest sized, which is largest, means what here? Atom. Which one has largest size among the third period elements here? Sodium or argon? Sodium only, remember. Sodium has what? Largest size. Sodium has largest size. Then what? Argon. After that, least size is what now? Cl. Least size is for what? Halogens. In any period, the least size is for halogens. That point keep in mind. Okay. So next now here, if you take ionization energy, if you take what now here, the concept of ionization energy. If you take now here phosphorus and sulfur. Phosphorus and sulfur. Now phosphorus size, suppose this much. Okay. It is what now here phosphorus size. This phosphorus and this is what now here sulfur. Now which one is small sized here generally? The sulfur is small sized than phosphorus. Though sulfur is having smaller size. Okay, when small size is there, IP value should be more now, but IP value of sulfur is not more. The IP of the ionization energy of phosphorus is greater than the ionization energy of what? Sulfur. Okay, here which one is the smaller size here? The sulfur is smaller size than what? Phosphorus. Though sulfur is having smaller size than phosphorus, the phosphorus only has what? More ionization energy. The reason what in phosphorus 3s2 3p3 half filled configuration is there. 3p3 is half filled. But here in this case of sulfur, what here? 3s2 3p4 we take. 3p4 is neither half filled nor completely filled. 3p4 is neither half filled nor completely filled. That's why 3p4 will be what now here? Less stable electronic configuration. But 3p3 half filled configuration is what? More stable electronic configuration. So because of more stable electronic configuration, it is difficult to remove electron from phosphorus atom. Therefore, the phosphorus has what? More ionization energy than sulfur. Though the size of phosphorus is larger than the size of sulfur. So like the anomalous properties will be there here. Sizes will be same order, but here ionization energy will not be following here. So ionization energies do not follow regular trend across the period. From left to right in a period, the ionization energies do not follow a regular trend. That means what? Continuous. Here, what we wrote here, ionization energy in the periods from left to right is increasing, we said generally. Generally, we said. But actually, correct point is what now here? Ionization energy values do not follow a regular trend from left to right in a period. Explain, they ask you. Then we have to take example of what now? 15th group element and 16th group element. 15th group element, 16th group element. We have to say. Next, here if you take magnesium and aluminum, the magnesium size is more than aluminum size. Magnesium size is greater than aluminum size. But again here ionization energy of magnesium is greater than ionization energy of aluminum. Generally, if size is less, we think that IP value will be more for aluminum. But here actually IP value of aluminum is lesser than what? IP value of magnesium. Though size of aluminum is smaller here. Why the answer is what now in this case now? In case of magnesium, 3s2 is configuration. In case of aluminum 3p1, the outermost electron, the last electron, differentiating electron is in 3p1 orbital, 3p orbital. Here differentiating electron of magnesium, 12th electron of magnesium is in s orbital, 3s orbital. In 3s orbital, the differentiating electron of magnesium is there. The differentiating electron of aluminum is in 3p. Okay, now here, if you want to remove electron from 3s2, okay, we have to remove electron from s orbital. If you want to remove electron from aluminum, we have to remove electron from p orbital. So here it is difficult to remove electron from 3s2. Why? 3s2 orbital, 3p orbital, 3s and 3p orbitals if you take, which will have more penetration power. Penetration power. The penetration power order is what? S orbitals more than p orbitals greater than d orbitals greater than f orbitals, which are more penetrated s orbitals towards nucleus. Now, which electrons will be strongly attracted by nucleus? S orbitals are closer to nucleus. If you take 4s, 4p, 4d, 4f, which orbital is very close to nucleus? S orbital. Which is away from nucleus? 4f orbital. That means when s orbital is taken in any orbit, in any shell, if s orbital is taken, it will be closer to nucleus relatively. When s orbitals are closer to nucleus, we say penetration power of s orbitals is greater. When penetration power is greater, the electrons in s orbital will be strongly attracted. See here, 3s2 is third orbit, 3p also third orbit. Now, here in case of magnesium, we are removing electron from 3s orbital, which is more penetrated. That's why it is difficult to remove electron from 3s orbital. That's why more IP value should be supplied here. More ionization energy is required to remove electron from 3s orbitals than from 3p orbitals. So what we have to take now here, in case of magnesium, stable electronic configuration is simply. In case of magnesium, stable electronic configuration, why? More penetration power of 3s orbital. Due to more penetration power of 3s orbitals than 3p orbitals, it is difficult to remove electron from 3s2 orbital of magnesium. Therefore, magnesium has more ionization energy than what? Aluminum. So this point keep in mind. So it's about what now here, the important points, the variation of periodic properties across the period and down the group. We have to understand. And if you take now fluorine, chlorine and chlorine. Now generally fluorine size is smaller, Cl size larger. Now but electron affinity of fluorine is smaller than electron affinity of Cl. Electron generally, when size is less, electron affinity should be more generally. When size is less, electron affinity should be more. But in this case of fluorine and Cl, what is having more electron affinity? Cl is having more electron affinity, not following regular trend. Okay, the reason what here, due to very small size of fluorine, here 7 valence electrons, 7 valence electrons, 1, 2, 3, 4, 5, 6, 7. 7 valence electrons in small sized second orbit. Okay, due to very small size of fluorine atom and due to inter-electronic repulsions. Between electrons, repulsions will be there, which are called inter-electronic repulsions. There are greater inter-electronic repulsions in fluorine and very small size of fluorine. Because of these two reasons, the fluorine has what? Less electron affinity than what? Cl. The same thing we apply for oxygen, sulfur. Here also oxygen size is smaller, sulfur size is larger. But oxygen has less electron affinity than what sulfur. The same reason, due to very small size and greater inter-electronic repulsions. Okay, oxygen has less electron affinity than sulfur. So this point we have to understand here. So this is about variation of periodic properties across the period and down the group. Okay, remaining points you have to read the textbook lesson once you read and material bits also do once. Okay, bye. All the best now.